halogenation. So you have alkane, carbon-carbon double bond. So always, let me stress that you got to focus on this. No matter how large alkene molecule you have, you got to focus the double bond. Right? That's the reactive center you have. So if you do the halogen addition, which is halogenation, so you're gonna have the chlorine or bromine added to the carbon, right? That's the expected one. So that's why you're gonna have the bromine added to one double bonded carbon, and then another to the other double bonded carbon. And then you know how to calculate the oxidation number, right? You have the formula. So count the valence electrons. So for carbon, it's going to be always 4, right? And then you're going to have the minus how many electrons it owns, right? Either lone pair or bone electron, whatever you have, depending on the electronegativity difference. Right? So that's how we're going to calculate it. But today, we don't want to go to the math. We're going to see more reactions of this type. Right? So this is going to be all oxidation reaction. So if you calculate the oxidation number, you're going to find out the loss of electrons for the carbon in all reactions, right? I mean, in this chapter, I don't mean all Ocam 1 reactions, but for alkene reactions, we're going to deal over here, going to be oxidation. Okay? So now, if you see another example, this one as an example, so this is cyclic alkene, right? So where are you going to focus when you do the halogenation for that? So you're going to focus over here, right? So double bond. So this part, that's the center. So you have bromination there. So you have Br and Br. Right? So what are you going to do? You're going to add one bromine to this carbon. So you have this. And then other one to the other carbon. So you have this bond. Right? So this is the halogenation. Now, if you compare this with the hydrogen halide addition in the last chapter for the same alkene, so what was the product? So if you had, you can compare that. Say if you had that, you do the same thing, right? You're going to add hydrogen to the one double bonded carbon and then bromine to the other double bonded carbon, right? So here you have the hydrogen and bromine, different atoms, so it matters where hydrogen goes and bromine goes. That's why you have the Markovnikov's and anti-Markovnikov's rule on that, right? But here you have both bromine, doesn't matter where you add them, right? You can add one bromine to one carbon, other to other carbon. So what's going to be the product? That is going to be the alkane derivative, right? So dihalide, you have the two halogen atoms on two carbons of alkane, right? So alkyl dihalide, that's the product you're going to have, right? Which alkyl depends on which reactant you have. Can be 2 carbon, 5 carbon, any branches, any cycle, doesn't matter, right? So you're going to be dihalide, okay? So this is halogenation. So now, if you see the mechanism of that, now it is a little bit different than the previous chapter. H Br addition, right? So if you recall, what was the mechanism for the hydrogen halide addition to alkene? You had two-step mechanism there, right? Number one, you're going to use the pi electron to make the bond with hydrogen. So you have the carbocation intermediate. Number two, you have the nucleophile, which is Br minus. You're going to add that to the carbocation center, and you have the product, right? Two step. But here, you're going to have all in one step. This is called like a concerted reaction, right? So the mechanism going to be, you can call that this. So everything is going to be simultaneously. So it's not like one going to be formed and then after that another going to be formed. So all in the same time simultaneously. So this is concerted. Okay. So how we're going to form is like this. So bromine, you have the lone pair, right? You know that. You have 3 lone pairs there. So you're going to use the pi bond like before to make the bond with the bromine. And then you have the other lone pair. So actually you're going to have 2 bonds with the bromine. Right? So, and then you're going to have the another center with the nearby bromine you have. So you're going to have the 2 bromine there. Okay? So this is simultaneous. So first, you're going to have the bridge type of bonding with 1 bromine, and then another bromine comes after that. So you're going to have the 2 bromine on 2 carbon atoms. Right? That's the mechanism. Okay? So remember for the oxymercuration in the last chapter, I said we're going to see in the next chapter. So this is the mechanism for that. Okay? So exactly same. So the mercury gonna be like bromine. So mercury gonna be the bridging atom, and then you're gonna have the OH after that. So you're gonna have the compound, right? So that's the alcohol formation. So this is gonna be exactly as halogenation. There is no difference at all. The same step with the bridging between the 2 carbon atoms. Okay? So this is not hard. Don't think this is a very hard one. So simply remember you have the double bond there. So pi bond gonna make the bond with the bromine, right? And then bromine is gonna have lone pair. So it's gonna make the bond with the other carbon. So 1 bond, this gonna be from the pi bond. So this is pi bond you have. And then the other one is from the lone pair. This one. That's why you have the plus over here. Because it used the lone pair it has there to make the bond. This is just instantaneous. It cannot be that stable. So other bromine is gonna go after that. And you have 2 bromine bonded. Right? That's the mechanism. So here, one thing you need to be very careful is what type of product you're going to have. Cis type or trans type. We're going to call the syn product for that. So this is like a trans. So you're going to have 1 bromine to the one side, other to the other side of the ring. Or you can say plane of the double bond. So if you have the plane of the double bond, 1 bromine is going to be to one side, other going to be to the other side, opposite, like a trans, right? So that type of product going to be formed. You can never have cis type. Okay? So why this going to happen? Because of the orbital orientation. So once the 1 bromine is bridged, for the second bromine to go after is from the opposite side. Because whenever the bromine is raised like that, the orbital is going to be on the opposite side of that bromine. That's the reason why this is the only place the other bromine going to find carbon to make the bond with. Okay? That's the reason why you will not have like that. You're going to have like this. Trans type. Okay? So that's the mechanism. Or you can compare the energy, like a why the cis type doesn't form. So this is from the experiment. So you can see the EA value for that. It is so high. It means you need to break the bridging bond to overcome that. Right? So since it is too high, it is not favorable to go this route. So you're gonna go from here. So that's gonna be deformed. Trans gonna be deformed. Okay? So that's the mechanism. So if you think mechanism is too hard, first remember the product. Okay? This is very easy. You have the carbon-carbon double bond. You have the bromine molecule, and you have two bromine atoms, right? One atom go to one carbon, other goes to other carbon, right? Just remember you're gonna have like a trans type, not the cis type. Okay? That's the product you're gonna have, right? Did I make it a little bit easier? Okay. So now, here, if you see that, you don't see any other than the bromine, right? So here, so you have just the bromine, you don't have any other reagent, right? Do you see any other reagent? No. So now, for the same reactant, if I add water over here, add solvent, okay? So now you're going to have the different product. So if you don't have solvent, just the bromine reactant there, then this is the product you're going to have dihaloalkane, right? But if you have water there, so this is what it's going to form. So it's going to form the halohydrine. That's the compound. So you're going to form this. So you can write for simplicity Br2 and H2O. So remember this. So this is must for halohydrine. Now halo gonna be halogen, right? So chlorine, bromine, this is obvious. Hydrine is you're gonna have the hydroxy group with halogen there. Right? So then what you're gonna have? So bromine like before, you're gonna have one that, and then the OH is gonna come from water. So you can have bromine and OH group there. This is called the halohydrine. If you have the bromine, it's gonna be bromohydrine. If you have chlorine, that's gonna be chlorohydrine. Right? So chlorohydrine, bromohydrine, in common, this is going to be the halohydrine. So that's the compound. So now, if you think why it's going to be formed, so the reason for that is you're going to have the same mechanism like before, like halogen addition. You're going to have the bridge between the carbon and bromine, okay? And then you're gonna have the bromine minus nucleophile. So before this goes over here to the carbon, water molecule gonna go there. Because bromide is more stable. So water molecule or the oxygen center quickly goes there. So you're going to have the OH there from water instead of from Br minus. That's the reason. Okay? So this is bromohydrin. So remember the reactant combination. Bromine with water. That's the bromohydrin. Right? So I need a little bit practice in that. So another reaction is epoxidation. So epoxy addition, right? Epoxy, you can say addition like that. So what is epoxy? So epoxy is something like this one. So you're gonna have oxygen bridge with carbon. If you have that, it is called epoxy. Okay? So you're gonna form that. So how are you gonna form? So initially you have something like this one. So you have the double bond, right? You're gonna need some reagent. That's gonna give the oxygen to make the bridge over there. Right? So you're gonna put reagent like that. The oxygen donor. Okay? So what's gonna be? One very frequently used is that. So you're gonna have the hypochlorous acid, HClO, you can write that, HClO. So this is hypochlorous acid, right? So one is that. Other, you're gonna have the oxychloride. We're gonna go later after this one. So first, let's see HClO, or you can say HBRO. This is also gonna be same thing, right? So this is gonna be hypobromous acid. If you have Br there, so either one is gonna be fine. So you're gonna use that. So what's gonna happen is the oxygen of this gonna go here and then breathe as carbon oxygen in the product, right? So this is called the epoxy formation. So you have just HCl over there, something like that, right? So that's the epoxy formation. So these hydrogens, so you don't need to worry about that. So this is just the initial hydrogen on the alkene. You have hydrogen over here, right? So that's what it is showing over here. It's not new. So only difference is you're gonna add oxygen on the double bonded carbon. That's what you are doing. So don't be confused with hydrogen shown over there. Okay? Alright, so another reagent for the same product is this. So something like this one. So this is called MCPBA. So this abbreviation comes again and again. You're going to use it in different reactions, right? This is metachloroforbenzoic acid. So ortho, meta, para, we're going to see in the what is called the aromatic compound later. You're going to go in detail in OChem 2. So the position of the carbon. So if you have something in the ring like that, you have double bond. So if you have some group, say R, so this is gonna be ortho, this is gonna be meta, this is gonna be para. So that's how this para comes from, meta comes from, right? So ortho, meta. So this is gonna be ortho, this is gonna be meta, this is gonna be para. So that's how the name comes, but we're gonna go in detail on that. So that's the name of the compound, right? So if you have this, MCPBA, so this is gonna give the same product. Why? It has the oxygen to give, right? So you're gonna have this oxygen added over here, like HClO. So the oxygen donor is the one you're gonna need to have the product. So this is the product here, right? So again, this is the consorted light halogen addition. you're going to have the bridge formation and then the bond breaking of the reactor at the same time, simultaneous. Good? So just remember the reagent. That's why you need to remember. Either this one or HXO, HClO, HBRO, like that. Okay? Okay, so now another is dihydroxylase. Now you have the di, so you have the 2, right? And then you have the hydroxy, that means OH. You have the addition. So you have the alkene. In alkene, what you're going to do is you're going to add 2 OH groups over there. One OH in one double bonded carbon, another OH in other double bonded carbon. That's what it means, just from the title. Okay? So now, what you need to have that? Obviously, you're going to have the OH, right? So you have the double bond. So you're going to put one OH over here, like that, and then the other to the other carbon, like this one. Right? So 2 OH addition on the double bonded carbon atoms. So this is dihydroxylase. So for that, you're gonna need the oxygen source as well as you're gonna need something that's gonna give the hydrogen for that. 2 things, right? So you're gonna use the oxyum oxide. So this is the tungsten metal, OS, and then you have the oxide of that, like iron oxide, palladium oxide, like that, right? So you're gonna use that metal oxide. So it's gonna make the bond or bridge like before with the carbon. So now you have the oxygen as required over there. So the next thing is you're gonna remove the metal part and then you're gonna put the hydrogen in it, right? So that's where this comes in. So this is gonna give the hydrogen with oxygen. So this hydrogen, and then the other byproduct, metal part, gonna be there. So this is the main product you have, right? So 2 hydroxy group addition. You need metal oxide, osmium oxide, and then you're gonna have the sodium hydrogen sulfide. Of course, it's gonna be the solution. So you have the water there. So solution of sodium bisulfite solution, right? With water. So that's what you're gonna need. So mechanism, the same thing, right? This is consorted like before. So all gonna be at the same time. So this is also like before. You're gonna have the syn or trans or cis type, 2 different types, right? So here you're gonna have the syn type, like a cis type. So you're gonna have both on the same side of the plane towards the beer you have, right? So this is gonna be the product. Remember, this is different than the one we saw before for the dihalogenation, right? So why do you think gonna be different? Remember, in the dihalogenation, you're gonna have the 1 bromine bridge, and the second bromine gonna make a bond from the other side of the plane, right? From the lobe below the plane of the ring you have. But here you have bridge of 2 oxygen from the beginning. It has to be planar. So we're gonna be on the same side to make the bond. So in the final form, you're gonna have on the same side. So that's the difference. Okay? Yeah.
Can you explain again why they're not going in different directions, the oxygen
Okay.
compared to the
Let's make it a little bit easier. So, this is one plane, right? So, let me show you the previous reaction first. This one, okay? So, this is the plane of the double bond you have. So, now you have one bromine to make the bond with these two carbon atoms you have, okay? So, bromine has to be, say, over here on one side of the plane. So, you're going to have the bond with two carbons in the plane over here. Okay? So, now for the second bromine to make the bond, either it can make a bond with the left carbon or the right carbon on the plane, double bonded carbon, right? So, both are engaged with one bromine on one side. So the only lobe or the orbital available is opposite to the bond you have on the back side. So you have the lobe on the back side. So it has to come from the back. So you're going to be other side of the plane you have. Okay? So that's what you're going to see over here. This is on the other side of the bromine. So if you have the bridge towards you, lobe going to be over here on the back. So it's gonna go, other bromine gonna go from the back. That's why you have the trans type for here, right? Because it is one after another. So now, if you go over here, so you have the two double bonded carbon as before. You have the same reactant, okay? So now you have the osmium oxide. So you have the 4 oxygen over there. So 2 out of 4 gonna make the bond with the double bonded carbon, right? So you cannot have like a one oxygen bonded this side and then the other oxygen bonded to the back side because it is the same molecule, right? So same molecule cannot be back and forth, either from the front or from the back. So from the beginning, both oxygens gonna be on the same reagent and then bonded on either front or back. So it is on the same side from the beginning. So there is no way of having trans type. Okay? That's the reason for that. Okay. So now, other gonna be other oxidizing agent, so you can also use this. So this is the same hydroxylation. You can have the KMNO4 reagent, so you can have the product, right? OH. So this is a little bit less hazardous compared to the other one. So you can use this to test in the lab. Okay, so with other one, we don't use it. So this one, normally, suppose you have the unknown compound, if you don't know whether it is alkane or alkene, if you cannot distinguish that, so this is used. So if it is alkene, then you're going to have the dihydroxylation reaction. So now you have the proton there, so it is acidic. At the beginning, going to be basic. You have the basic solution there. So at the beginning, the color gonna be like a pinkish color, right? So in a base, if you put indicator, it's gonna be the pink color. And then when you add acid, then once it's neutralized, then it's gonna be colorless, right? So colorless to slight brownish. So if you add more, gonna be brownish. Just for the neutralization, gonna be colorless. So if you have that color change, then you say the unknown compound is alkene. If it doesn't change in color, then that means it is not alkene, so maybe alkane or other, right? So that's how you can test in the lab. So this is the qualitative testing for the alkene. So this is sometimes in the OPM 1 lab we do this, but here we're not doing it, but we can do it in the lab. Okay? So this is the same product. You're going to have the dihydroxylation. You can have the potassium permanganate. in addition to the other group. Okay. This is 1. So now, if you have the dihydroxylation but with the trans, if you don't want to have the cis like before or syn type, if you have the trans type like the dihalogenation, so you're going to use the different reactant for that. Okay, so this is the reactant. So you are not using the osmium oxide, you are not using the potassium permanganate, you are using the different reactant. Okay, so from there you can have the trans type. So one gonna be in one side, other gonna be to the other side. It's gonna do like a bromination mechanism. So addition of one first, followed by the other one. Okay. So that's the difference. So same type of product, but just the stereochemistry is different. So in which side of the plane you have the OH group attached. Same side, you're going to choose one class of reagent. You're going to have to the opposite side, you're going to choose this one. MCPBE, remember we see this before, right? So that's what you're going to do. So the next one going to be the ozonolysis. So what is ozonolysis? So you're going to see addition of ozone. That's what it means. Right? So you know what is ozone, right? So this is O3. You see this molecule in Genchem, probably Genchem 1. When you have the resonance definition, so this is the typical example you saw there, right? So you have the O and then double bond and then single bond. So you can have the shift in the double bond. So now you can have the double bond to the other side and single bond. So you saw that. This is ozone, right? So if you react ozone with alkene, now you're going to have the very different product. Right? So it's not alkane, not alkene. So you're going to have the carbonyl compound, like something like this one. So here you're going to have the CO double bond, and then you're going to have the 2 hydrogens on carbon. So for this case, you're going to have the formaldehyde. That's the name of that. If you have both alkyl group, like this one, for example. So you have the R in one side of the carbon and then a hydrogen to the other one. This is called aldehyde, right? This is aldehyde. This is formaldehyde. And then if you have both, like this one, this molecule, you have the carbon, you have the oxygen, and you have both R. So R can be any alkyl group, okay? And just like R is the notation for any alkyl, methyl, propyl, butyl, whatever you have, any branch. So if you have that, that's the ketone. So that's the name. So in common, for all these 3 types of molecules, we're going to call carbonyl. So carbonyl molecule, carbonyl functional group, we can call that. Okay, so that's the product you're going to have. So now which product you're going to have, either formaldehyde or aldehyde or ketone, it depends which reactant you have. Okay, so if you have the unsubstituted alkane, like this one, this is ethene, this is the simplest one, right? So this is ethane, so this is gonna give the formaldehyde always, not substituted alkane, right? And then if you have the substituted one, not completely, but partially. So you have the one hydrogen over here for number 3 carbon. This is not substituted. But other hydrogen is substituted by the R group. If you have the partially substituted alkene, they're going to give the aldehyde, right? They're going to give this. If you have both substituted or the complete substitution alkene, you're going to have the, like something like this one. So you're going to have the ketone from there, right? If you have the complete substitution like this, let me write the different column so that this confusion. So like this, you have the both substitution, right? If you have that, you're going to have the ketone like that. That's the difference. Okay, so ozone, if you react with alkene, you're going to have the carbonyl product. Which carbonyl? It depends which alkene you have. Either not substituted at all, or partial, or the complete substitution. So that's the product you're going to have, right? So you're going to see the mechanism, how this product is going to be formed. So now you're going to draw the ozone, right? So this is ozone. So this is ozone, like O3, right? So this is the structure you have. You have the 3 oxygen, 1 double bonded, and 1 single bonded. You have octets and all oxygen atom, right? So this is ozone, and then this is alkene you have. So alkene is this one. So you are adding ozone on alkene. So now where we're going to start? Again, always double bond. That's the only reactive center you have, right? So then you're going to use the pi bond to make the bond with one oxygen and the other bond with the lone pair of oxygen. So obviously you're going to make the bond like this. So 2 double bonded carbon on 2 end oxygens of the ozone. That's like other reaction we see, right? Always you're going to take the double bonded carbon atoms. You're going to add reagent there. You're doing the same thing over here. So the end oxygen of ozone is going to be bonded on 2 carbons, right? So now you're going to have something like this. So this is intermediate. So you're going to have a little bit rearrangement over here. So this is same as this one. So this is intermediate, which is called ozonite. That's the name for that. This is intermediate, right? So something in the activation, or the, you can say the transition activation complex, right? Transition state. So now after this, to make the product, so you're going to have the second reagent. So you're going to have the, always you're going to have the combination. So you're going to have the O3 with, you're going to have something like this, dimethyl sulfide. So it is something like this one. So you're going to have sulfur, CS3, CS3 like this. Dimethyl sulfide is a solvent, organic solvent. So you're going to do number 1. So first you're going to do this, number 1, and then you're going to do number 2 for that. React with ozone first, second with solvent, right? So the function of solvent is to take the 1 oxygen out from the intermediate. So one of these is going to be taken out by the solvent. Okay? So then you're going to have the rearrangement with the other. So now this is going to be out from here. So now 1 goes to 1 double bonded carbon and the other goes to the other carbon. So you have two oxygen, you're going to divide half. One oxygen to one carbon, other to other carbon. So then you're going to have this. Right? So that's going to be the product. So one oxygen is taken by the solvent. So this is out from the ozone. So this is in the solvent phase. So you're going to discard that. And then the product going to be these two. So that's how it's going to be formed. Okay? So now, to just guess the product, it is very easy. Right? So what you're going to do is, let me go back. If you're going to guess the product, what do? You're going to break the bond of the alkene, and then you're going to add one oxygen for this carbon and the other oxygen for the other carbon. That's the product you have. Right? So break the double bond half in the center, and then put one oxygen for one double bonded carbon, another oxygen for the another double bonded carbon. That's the product you're gonna have. Okay, so that's an easy way of remembering that. Just remember the product. Shortcut, easy way. Okay. So now let's see one question. You can say practice question, right? So suppose in your test, this is the question. So you're going to figure out what reactant is going to be formed. So that reactant may be aldehyde, ketone, formaldehyde is also part of that. So probably formaldehyde is not option over here because you have the carbon substituted. Okay, you have the alkyl group over there. Anyway, so you're going to guess the carbonyl. From the carbonyl product, you're going to guess the alkene. So which alkene you're going to choose so that when you do the ozonolysis reaction, you have the O3 and solvent over here. First, add ozone. Second, react with the solvent. Then you're going to have the product. Okay? So this is product. So this is aldehyde and ketone, right? So this is aldehyde over here, and then this is ketone over here. So in combination you have the carbonyl products. Okay? So now how are you gonna guess the alkene? So you're gonna go backward. So from alkene to product, what you did is you're going to break the double bond and then put two oxygens to the side. You have the product, right? So now you're going to go back from the product. What do? So take the two oxygen out from the product, and then you're going to connect the double bonded two carbons together. There's the alkene you're going to have. Okay? So what I can do over here is let me see. So I'm gonna take this oxygen out and then take this out because these are added when you have the product, right? And then you're gonna connect these two carbons together. So connect these two together. That's the problem. That's the alkene you're gonna have, right? If I draw it, I'm gonna draw something like this. So I have the ring, benzene ring. I'm gonna write circle. Circle is same as 3 double bond over there. Okay. And then I'm gonna have the carbon. Okay. So let me show the carbon 1 and carbon 2 to make it easier. So you have methyl over there. So I have the double bond over here. I have the carbon number 2, just the labeling. And then I have the methyl, I have the hydrogen. if I take this alkene and if I do ozonolysis, what's going to happen? So I have O3 and then I'm going to have CH3 2S. This is the same molecule. We have two CH3 groups and then sulfur there, right? So dimethyl sulfide. So now what you do is you're gonna break this bond and then you're gonna add one oxygen to this carbon and then the other gonna be to this carbon, right? If I do that, so what's gonna be the product? So carbon 1 and then I have double bond over there, carbon 2 and then I have the hydrogen over here and double bond, right? That's the product. I have this over here. So this is this product and then this is this product over there. That's how you're gonna do, right? So you can either guess the product if you know the alkene, or you can guess the alkene if you know the product. Yeah. 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 So sometimes you can write this. So this, if you have the complete, so this is same as this one. We have the alternate single, double, single, double. So this is represented by the one sample. This is benzene. So if you have without any substitution, you have this is benzene. So this. If you have substitution, you're gonna have different name. We're gonna go in detail. You're gonna have separate chapters on this in OCHEM 2. You're gonna go all the nomenclature and then criteria to be this type of compound. We're gonna go in detail. All right. Any question on that? It's easy, right? Don't feel very hard. So just like think easy way. If you have like a larger molecule, it doesn't mean it is hard. So just remember the clue you have. So alkene. Whenever you say that, this is the one you're going to focus. Doesn't matter what substitution you have after that. Okay? Maybe a ring, maybe a branch alkyl group, whatever you have. So don't be scared of that. So alkene is this. Double bonded carbon. Right? So if you add O3 and then you're going to have solvent on that, what you're going to do is simply you're going to break over here and then in ozone you have a 3 oxygen, right? So add 1 oxygen to 1 carbon, right? And then the other oxygen to other carbon, that's the product you have. That's simple. Right? So focus on that. So just focus on the double bond. Doesn't matter how many methyl or propyl or ring you have, that's a substitution. You're going to keep that as is. You don't change any substitution there. The only thing you're going to change is break the double bond and then put the oxygen in place of that. Right? Carbon oxygen double bond. That's the problem. Right? Alright. I think we have a little bit, few slides remaining, so we're gonna do on Monday.